This will continue here.
Okay.
Professor Ansari is well-known figure, and I think there is no need to the introduction of the Professor Ansari. It has a good command in the variation equality, optimization, vector optimization, and more other areas, and he has several books, edited books, and some other books. So I invite Professor Ansari for his talk.
Thank you, Professor Sahu. Actually, during this December, I have already given 2 talks online, of course, and this is my 3rd talk. But I am not very much satisfied with the online conferences, online kind of conferences.
Of the
Because
conference on nonlinear applied analysis and
Professor Som, please mute your.
This is the morning session of 3rd day, parallel session.
Professor Som. Professor Som, can you mute your?
So now it's muted, sir. So you can continue.
No, still some kind of noise is coming. Dilip Kumar Ganguly, you please mute yourself. Dilip Kumar Ganguly, please mute.
Hello. Okay. Please continue.
Okay, now thank you. Okay, now it's okay. Now it's fine. Okay, so thank you very much. Actually, you see, as I mentioned, I'm not interested, and basically, in my opinion, the online conferences says do not solve the purpose of the conference. The purpose of the basic purpose of the conference is to have the interaction with each other. So as I mentioned that Professor Akhtar, he was here in Aligarh several years ago. I don't remember the year. And Professor Nuzet was also here. So they have the interaction, and then he went to Germany and so on and so forth. So, but somehow, anyway, at least by having this kind of conferences, we came to know that what the people are working, and especially the Professor Khan, he has given a very nice talk, and he has mentioned that there are many applications, real life problems that can be written in the stochastic partial differential equations, and such differential equations can be solved by using the variational technique. So it was very nice. So let me start my talk. Here is I shared okay. So I'm now going to give the talk on the variational inclusion on Hadamard manifold. So first, as you know that the variational inclusion, so variational analysis is one of the well-established subject in nonlinear analysis, optimization, partial differential equation, and several other areas. And many problems, as you have seen that the stochastic partial differential equation can be written in the form of stochastic variational analysis, and then you can use the variational technique, or you can use the extra gradient method to solve such problems. So here is I am going to consider the variational inclusion problem on Hadamard manifold. So that is important. There are 2 things. One is of course, I am considering this on the manifold, but why Hadamard manifold? So that's I am going to present here. So let us see. First is what is the manifold? So have you do you have any idea how do we prepare? How do we write the map of the globe on a sheet of a paper? So basically, here is we use the technique of the concept of manifold, which was used sorry by a cartograph sorry. So let's see, here is I just gave a manifold is used to describe spaces that may be curved. In other words,
Corey,
yeah.
Have you shared your screen? I cannot see your presentation.
I'm sorry. Okay. 1 minute. I forgot to share this. Thank you very much, Professor Wong.
I was thinking just it is introduction, so there is no need to slide.
Okay.
Maybe you want to speak like me without.
Yes. Okay.
Oh, thank you. Yeah, I see it.
Yes. Now you can see.
Yeah, no problem. I see it.
Fine.
Okay. I'm sorry, I forgot to share the screen. So let's see what is a manifold. Usually, a manifold is used to describe spaces that may be curved. In other words, you can say that in manifold is a topological space that is locally resemble with Euclidean space near each point. For example, if we consider a point over here, then you will see that here you have a rectangle. Similarly, if you take a point here, you will have around this point you have a rectangle. So here you can see also around here you will have a rectangle. So that is to say a manifold is a topological space such that around every point we can choose a small region that is shaped like an Euclidean space. For example, if we take a circle, okay, a circle is one-dimensional manifold embedded in two-dimensional space where each arc, you see this arc of the circle is locally resembled with a line, and same as a sphere is a two-dimensional manifold. The sphere, of course, a sphere is a three-dimensional in the Euclidean space, but it is a two-dimensional manifold embedded in three-dimensional Euclidean space where each patch, you see here is each patch of the sphere is locally resemble with a segment. You can see here is this is the plane segment. So what is the proper definition of a manifold? So let me start with the proper definition of the manifold. So an n-dimensional. So here is, look here is this n. So I will explain why we have taken this n. So n-dimensional manifold is a Hausdorff and second countable topological space that such that every point x in M has a neighborhood U and a homeomorphism phi from the open set U onto an open subset of Rn. So whatever is with this n is same as this n. So if you have the homeomorphism from a topological vector space to Rn, then it is n-dimensional manifold. And if we take the collection of the neighborhood and the homeomorphism, the pair of open neighborhood and the homeomorphism, it is called the chart on M. And the collection of all charts, it is called atlas on M. For example, let us take this yellow figure is your M, is your Hausdorff topological space, which is the second countable. And suppose here you have a point, and this point has a neighborhood U and another neighborhood V. And from this neighborhood U, we have an homeomorphism from U to Rn. So it maps, this maps from here to phi of U. And this figure, this area is mapped on this one. Similarly, from here, we have a homeomorphism psi from this open set or open neighborhood of the point over here to this one. And then you can see that because phi and psi both are homeomorphism according to our here is a homeomorphism. So these are homeomorphism, that is to say they are continuous and their inverse is also continuous, and therefore we can see that this portion is mapped from here to here with respect to this homeomorphism, and this area is mapped from here to here with respect to this homeomorphism. So if you would have this map from here to here or the map from here to here, if these maps are differentiable, then we say differentiable again in the sense of Frechet. If these maps are differentiable, then we say that the manifold is a differentiable manifold. For example, we can consider the region. Here is we are considering this is the U around the Punjab and Chandigarh, you can see, and then we can have an homeomorphism and we can map this U to this region Punjab. You can see here is, and let's see here is we can have here we have a Chandigarh. So Chandigarh lies if you consider the Punjab as a neighborhood of Chandigarh, and then again you can see that Haryana is also a neighborhood of the Chandigarh. So we will have a homeomorphism.
আপনি শুনতে পাচ্ছেন কিছু?
Yes.
শুনুন, ভুল লিংকটা চলে গেছে আপনার কাছে, ওটা অন্য লিংকে জয়েন করতে হবে।
Yes. Any problem?
No, sir, it's okay. You can continue.
Okay. So we have a homeomorphism phi, and that maps from this neighborhood to the R2. Here is okay. So here is we have similarly from here we have this is your Haryana. So this is part is the Chandigarh, and this part is also Chandigarh. So that is the common part. So if we have this map and this map both are differentiable, then the manifold is a differentiable manifold. So now let's see what is the proper definition of a n-dimensional differentiable manifold. So let us take here is M is the n-dimensional differentiable manifold, and for each M Txm we denote for the tangent space of M at the point X. So basically you see, as I mentioned in broad sense, a manifold is a curved surface. So at each point we can have tangent spaces. So if we collect all the tangent space, or we can tangent planes. So if we collect all tangent planes, that form the tangent space. And the very important thing is that this tangent space is a vector space. And not only this, the dimension of that vector space is same as the dimension of the vector of the manifold M. So here we can take the advantages of being this tangent space a vector space, and then we can define the inner product on the tangent space. And we can use, and then if we can define the tangent inner product, and then we can use some properties of the inner product. So here is the very important thing is that we are lucky that we have this space is your vector space, and we can define the inner product on the tangent space, and then some of the properties of the Hilbert space or the inner product space can be used over this space, not over the manifold, but just over the tangent space. If we take the collection of all tangent space, that is called tangent bundle. So we define the inner product. As I mentioned, this is your vector space. So we define the inner product. So this is the inner product. So if this is the inner product, then it is called a Riemannian metric on the tangent space Txm. Okay, and corresponding to this norm, we will have corresponding to this inner product, we will have the norm, and which we write in this way. If they okay, so and now a differentiable manifold with the Riemannian metric. So the Riemannian metric is called a Riemannian manifold. For each point X and Y in M, let gamma be a piecewise smooth curve joining X to Y. Then the length of the curve can be defined in this way. You take the integral from A to B, gamma dash with this derivative dy d gamma over dt t, and take the norm, and this is your dt. And now we define the Riemannian distance from X to Y. So we take the infimum, because here is you see this is a piecewise smooth curve joining X to Y. So there may be several piecewise curves joining X to Y. So we take the infimum of all such curves, okay, length of all such curves. So that is called the Riemannian distance between X to Y. And I'm not going into the definition of the Levi-Civita connection. So if this is whole, we have the definition of the geodesic. Again, if I go to the definition, then it will be a problem. So a geodesic joining X to Y in M is called a minimizing geodesic if its length is equal to the Riemannian distance. Now, a Riemannian manifold is complete if for any point in M, all geodesic starting from X are defined for all T in R. Okay, so this is the definition of the completeness of a Riemannian manifold. Then we have the parallel transport. The parallel transport meaning is that actually if you have two curves or two geodesics on a manifold, then you cannot talk. So for example, here you have this is your curve, and then here at each point you have several tangents. So this is the tangent space. Now you have another geodesic. Here you will have a curve, but because this is another vector space, this is another vector space. So you cannot compare the vector space, the vector over here and the vector over here. So by using the parallel transport, what we do, we can mathematically transfer a parallel vector from one space to another tangent space. So that we will use to have the parallel transport. Now let's say here is, if suppose M is a complete Riemannian manifold and gamma is the geodesic starting. So here is this is your M is your Riemannian complete Riemannian manifold, and here this is your any geodesic starting from the point P with the velocity v. Okay, that is to say, if we take gamma at 0, so with the starting point, this means that the starting point of the geodesic is P. So starting point P and with the velocity v. So with the velocity v means that so it is a tangent at this point. Then we can define the exponential map from the tangent space, tangent space at the point P to M in the following way, that the exponential PV is equal to the value of the gamma function at the end point, because this represents the end point. In other words, you can see that if suppose this is the starting point and is going with the velocity v, so this is the tangent space, and then we can define the exponential map from here to here. So this will go to at the end point, that is the point Q. So this is the initial point, okay, because the gamma 0 is equal to P and is going with the velocity v. So this distance, so you see basically this distance from P to Q. So you take this is the Riemannian distance. Okay, so from P to Q is the Riemannian distance, and it is equal to the norm of inverse of exponential map, this one. Now this is very important result which we use and which provides the completeness of a metric space and the completeness of Riemannian the equivalence between the completeness as a metric space and the completeness as a Riemannian manifold. So, and that's why by using this theorem, we can use certain results. For example, we can use the Banach contraction theorem, because in the Banach contraction theorem we have only the completeness. So that completeness we can use, and instead of having the Riemannian distance, we can have the metric. So we can use the metric as the Riemannian distance and the completeness, and therefore the Banach contraction theorem also holds good here. The proof you can see is same if you just so here is M is your Riemannian manifold. Then the following statements are equivalent. That is, say exponential map is defined for all of T XM tangent space. Closed and bounded sets are compact. M is complete as a metric space, and M is complete as a geodesically complete. As I mentioned, geodesically complete, but for each point we have a geodesic. Okay. Then any of these four equivalent statements implies that for any 2 point can be joined by a minimal geodesic whose length is equal to the Riemannian distance between these 2 points. And as I mentioned that the Riemannian distance between x and y is equal to the norm of exponential inverse yx. So we can calculate the distance. Now, a complete simply connected Riemannian manifold of non-positive sectional curvature is called Hadamard manifold. Here is we have the connection between the cat space, inner product space, metric space, and Riemannian manifold. I'm not going in the detail of these things. So, and this proposition is also a very important one in the sense that the exponent, the geodesic can be expressed in the form of exponential map. So suppose M is your Hadamard manifold. Keep in mind this is not true in the Riemannian manifold. This is true only in the Hadamard manifold. Then for any x, the exponential map is diffeomorphism. That is to say, the exponential map is continuous and its inverse is continuous. So we have the continuity of the exponential map, and this continuity we can use later. So this is very useful. The inverse and the exponential map and its are continuous. The second thing is that for every 2 point in the Hadamard manifold, there exists a unique normalized geodesic. There exists a unique normalized geodesic. That is to say, with the minimum distance, and if we take the norm, that is equal to 1. So it is starting from 0 and is going to 1. So we have a unique distance. And not only this, that unique normalized geodesic can be represented in the form of the exponential map. So here we can write it in this way. So this theorem is very important, and it is not means true in the setting of the Riemannian manifold, and that's why we take the advantages of this proposition to work on variational inequalities or optimization problem on Hadamard manifold. Instead of taking the Riemannian manifold, since this theorem is not true, so we will have to consider
Hello, Professor Ansari. Okay.
Excuse me. Actually, there was a power cut, so there was no internet. Now I connected with my this hotspot. So now, can you hear me?
Yes, fine.
Okay, yes. So this is fine. So okay, so we can we have this result. So now the question is, why are we studying the variational inclusion or variational inequalities or optimization problem on Riemannian or on Hadamard manifold? The story is a little bit longer. The first time I met Professor Tamas Repsak in Irche. It was in 2003, and he gave a talk on optimization on Riemannian manifold. Of course, I could understand a little bit, but not too much. We have 2-3 courses in MSc on Riemannian manifold and other kind of manifolds. But it was very difficult for me to understand his whole talk. Then we invited Repsak in 2006 at King Fahd University of Petroleum and Minerals, Tehran, Saudi Arab. He visited there and he gave talk, and we had a lot of discussions on the same topic, that optimization on manifold. Again, it was so difficult for me to understand. And after that, in 2012, I visited Taiwan Professor Wong is here, his university, and there was a Professor Chung Lee. He is an expert on optimization and variational analysis on Riemannian manifold. He used to consider Riemannian manifold, not to the Hadamard manifold, because if you are considering the problems of Hadamard manifold, and then because of the previous proposition, it is easier. So we had each day we go to coffee shop and discuss with this all these things. And then I realized that this is a new topic and we can work in this topic. And since then, we have 3 PhD students. One is Munirul Islam. He has completed his PhD on the same topic. The second one is Firoz Babu. I mentioned the work is with Firoz Babu. And the third one, recently he submitted Mohammad Zishan. And the fourth one is working on the same topic. And then I don't want to work too much on the same topic. So I will go maybe in the direction of our friend Khan. Just he has given the talk. So now the question is, why do we work on the Hadamard manifold? The idea is that in the recent past, you can see that many techniques, methods from mathematical programming, from nonlinear analysis, have been extended to the Riemannian or Hadamard manifold. The main advantage, of course, one is advantage is we are working in another setting, but the main advantage is that a non-convex problem can be transformed into a convex optimization problem. So you know that the convex optimization problem is always easier to solve rather than the non-convex optimization problem. So and the second thing is also the constant optimization problem can be transferred into an unconstant optimization problem. So that is you can see that let me describe the convexity in the manifold. So a subset C of a Riemannian manifold M, it is called a geodesic convex if for any 2 point the geodesic joining X to Y contained in the set C. Same as in the Riemannian, in the Euclidean space. So we have the line segment, and here we have the geodesic. So a function f from M to R, it is called a geodesic convex function. If for any geodesic gamma, the composition map is convex in the usual sense. And now you can see here is, if I take the function f of x is ln x. Okay, so the graph of this is this one, and this is the epigraph of the function f. And now if we consider this function in the Euclidean space, then you can see that this epigraph of the function is not convex, because if you consider 2 points u and v and join these points, the line segment joining u and v does not lie in the epigraph of f. So the epigraph of f is not convex, and therefore the function is not convex. Okay. Similarly, but if we consider the same function in the Riemannian manifold, so if you take this R2 as the Riemannian manifold, and then you can see that every point in this epigraph can be joined by a geodesic, even by a unit geodesic. Okay, and therefore this is the geodesically convex. And so this is geodesically convex function, but here it is not. For example, let me consider the minimization problem on a Riemannian manifold. So let's take this is the minimization problem on the Riemannian manifold M, which is described in this way. And let me have this function f is a non-convex function, which is described in the following way, that it is equal to sum of n and xi. And we can invoke the Riemannian metric in the following way. So here is we have this here, we can define the inner product in this way. And then we can see that M is a Riemannian metric, and it is not only with this Riemannian metric, M is a Hadamard manifold, and the tangent space is equal to whole Rn, and with the geodesic defined in this way. And then with respect under these settings, you can see that the F is a geodesic convex, but in other way, it is not convex in ordinary sense. So that way we can say that a non-convex problem can be non-convex problem can be considered as a convex one in the setting of Riemannian manifold or in the setting of Hadamard manifold. That is one of the main motivations to consider the variational problems in the setting of Hadamard or Riemannian manifold. As I mentioned that we are considering the variation equity on Hadamard manifold because it is easier than to consider the variation equity on the Riemannian manifold. Because in the Hadamard manifold, we can we can express the geodesic by in the form of the exponential function. So here is in 2003, Nemeth considered the variation equity problem, which is to find x in C such that the inner product of Ax bar and this exponential function, this is greater than or equal to 0. So that was the first paper in 2003 on variation equities on Hadamard manifold. And now geometrically you can see that the variation equity problem, this can be formulated as to find x bar in C such that minus Ax bar in the normal cone. So normal cone is defined in this way. So if you look here as a normal cone, then we can see that the x bar, which is the solution of the variation equity, if and only if x bar is the 0 of x plus nc, because here from here you can see that this nc is the normal cone set valued map. So here is this is your set valued map. So if x bar is the 0 of a plus nc, then x bar is the solution of the variation equity problem. Now, and this is called generalized coefficient. And Nemeth also extended the Brouwer fixed point theorem from we can say from Rn to Hadamard manifold, and he considered C as a non-empty compact and geodesic convex subset of a Hadamard manifold M. Then he proved that every continuous map from C to C has a fixed point. And now we define the projection of a point in a Hadamard manifold onto a closed and geodesic convex subset C in the following way. That is, it is the collection of all points on C whose distance is the smallest distance from all other points on C. So the same, almost it is same as in the inner product space. If you go in the norm space, we can put it here as the norm, and here we also put it as the norm here. And then we have a theorem which provides the characterization of the projection. That is to say, if C is your closed and geodesic convex, then this map is a singleton set. Okay, so you will have a unique point, and for any x in M, if y is the projection of this, then we have this inequality. So by using this characterization, variation inequality problem can be written in the form of the fixed point of the map, this one. So we can write the fixed point of this one. So if this is continuous, and of course we have this is your this is also continuous. So this would be the projection, the continuous map. So here we can take is a compact set. So by using this characterization, we can prove the existence of the solution of the variation equity problem. And not only this, by using this characterization, we can also propose, same as in case of the Hilbert space, we can propose the projection method in the setting of Hadamard manifold. Now let's see, as I mentioned that the zeros, if x bar is the 0 of A plus nc, then it is a solution of the variation equity problem. Now, if we consider A plus NC, because this NC is a set valued map, so if we can consider A plus NC as a general set valued map T, then this generalized equation can be written in the form of a variational inclusion problem, which is to find x bar such that 0 lies in tx bar. So that is the main goal. So main goal, how to find the solution of this problem. So this problem you see here is we can see that if we define the subdifferential of a lower semi-continuous and judicially convex function from M to R or extended real line, then the subdifferential of the function f at x is the collection of all vectors in the tangent space such that this inequality holds good. And we can see that very easily that the minimization problem, this minimization problem, if we consider this minimization problem, then we can see that is a solution of this minimization problem if and only if 0 lies in the subdifferential of f at the point x. So here we have the characterization in terms of the subdifferential of the solution of the minimization problem. Now, the question is again, instead of the, instead of taking, because the subdifferential is a set valued map. So if we consider this as a t, so it means what? X in the solution set of this minimization problem if and only if 0 in t of x. So for this problem, Rockefeller in 1976 introduced the proximal point method in the setting of Hilbert spaces to find the solution of the problem, this problem 7. Okay, so that is the means 0 is in lambda n txn plus xn plus 1 minus xn, and of course there are certain assumptions on lambda n. Okay, to prove the basically one can prove the weak convergence of the sequence, not the strong convergence, but for the strong convergence you need a lot of other conditions. And this proximal point method was extended by Chung Lee and his co-workers, and the paper was published in Journal of London Mathematical Society in 2009. So he extended this proximal point algorithm of Rockefeller in the setting of Hilbert spaces, and this proximal point method takes this form in the Hadamard manifold. So here you can see that is the lambda n txn, so it is same as that, and but this term, these two terms are replaced by this term. And then of course they have developed the whole theory, the convergence of the sequences, and then provided several things. And then we have another form of the proximal point method is the inexact proximal point method, and it was also given by the Rockefeller, which is this one in the setting of Hilbert spaces. And this inexact proximal point method was extended by Tang and Huang in 2013. Okay, from Hilbert space setting to Hadamard manifold in this way. And of course, under certain conditions, they prove the convergence result. So here is the important thing is this is the error. This term is the error of the sequence which is satisfying this condition. Now, before going to, I'm going to give the regularization of the proximal point method. So before going to the regularization of the proximal method, I would like to mention some notions for a set-valued vector field. For example, let us take this is the collection of all set-valued vector field, okay, such that T, so for each x, Tx is a subset of the vector space, this one, and the domain of T is the set of all points x such that this is non-empty. So a vector field T is said to be monotone if this inequality holds good, maximal monotone if it is monotone and satisfying this implication. Okay, then we have the Kuratowski, upper Kuratowski semi-continuity of the set-valued map T from M to T. We say that T is the upper Kurzhausky semi-continuous at a point X if for any sequence Xn in the domain of T and Un in the bundle space of T such that Un in Txn, these two relations, so this Xn converges to X, Un converges to U, imply U in T of X. And upper Kurzhausky, if it is upper Kurzhausky upper Kurzhausky at each point of this one. And one can see that if a vector field T is maximal monotone, then it is upper Kurzhausky semi-continuous on M. Now we can define the resolvent, because resolvent operator, the resolvent of the vector field T of order lambda is a set valued map, this one which is defined in this way. And one can see that to find the solution of the problem, that is to say to find the zeros of the set valued vector field T is same as to find the fixed point of the resolvent of T. So this here is this one. Now by using this one, we can have we study the regularization method for the proximal point method, which we have mentioned. Since Hadamard manifold M is a complete metric space with the Romanian distance D, we have the following fixed point result. That is to say, we can fix U any fixed point in M as lies between 0 and 1 and lambda is greater than 0. Then we can then the map psi of X, which is defined in this way, is a contraction map. And by using, because this is the contraction map and therefore this would have a unique fixed point. So we proved this result. And then by using this result, because this has a unique fixed point, so we can have, suppose US is the fixed point of this one, so we can write in this way. And so by using the previous lemma, we established the convergence result of the net generated by this one to a solution of the inclusion problem as approaches to 0. So that is to see if U is any fixed point in M and lambda is greater than 0, S lies between 0 and 1, and T is your set valued vector field, which is a maximal monotone, and the domain of T is equal to M, and of course the inclusion problem, this has a solution, then the net generated by this converges to this point. That is to say, here we have a fixed point on M, and let us take the projection of that fixed point on the solution set of the solution set of the solution set of the variation inclusion problem. So then so the net will converge to this point. So we proved this result. Now we have the inexact proximal point algorithm. Okay, as so let's take here is T is your set valued vector field, and we can initialize, we can choose any initial point U0, and we can fix U, and then we start n is equal to 0. Let us define Un in this way. V is equal to this one and Un plus 1 in this one. And then so we have these two conditions where the this is your error term, so satisfying this condition and this condition. And then of course we can see that if we take M is equal to Rn, then the previous algorithm reduces to this one, which is considered by Shu here is in 2006, and Hong and Yang it is 2009 is this one. And then, of course, if again we can take m is equal to Rn, v is equal to Un, then the previous algorithm reduces to this one, which is considered in the paper of this one, Han and he. It was published in Journal of Mathematical Analysis in 2001. Of course, we can have some particular cases of our result. So if we take Vn is equal to Un, then we get then the algorithm 2.1 becomes the algorithm presented by Tang and Huang, as I mentioned in the setting of Hadamard manifold. And if we take Vn is equal to Un, psi n is equal to 0, then again our algorithm reduces to the exact proximal point method studied by Chung-Lee and his others. Then we proved the following result, following convergence results. If T is your maximal monotone vector field and U and Vn are the sequences generated by our algorithm, then the UN converges to a solution of the inclusion problem. So this we proved, and then we gave the application of our result to the minimization problem. As we have mentioned, this is always holds good. So we take the advantages of this, and now you can see that this vector, this here you can see that we will have basically to use the previous result, we need to have this lemma, which says that if M is your proper lower semi-continuous geodesic convex, then the subdifferential is a monotone vector field. And not only this, if the domain of F is equal to whole space, then the subdifferential is a maximal monotone. And in the previous theorem, you can see we are considering T is your maximal monotone. So with these two assumptions, the F is your lower semi-continuous geodesic convex, and the domain of this is equal to whole M, we will have the following algorithm for solving the optimization problem. And we have, of course, we can prove we have this one, and we can prove that the sequence generated by this algorithm converges to a solution of the optimization problem. Now we have finally we have this numerical result where we consider M is equal to this space, and M is, this is your Romanian metric, which is defined in this way. And then we can see that the Romanian distance D can be is equal to this one. With these settings, M is your Hadamard manifold. Okay, the details is given in the book of Urdiste. Okay, this in this book, and then we can take gamma is a geodesic starting from X with the velocity V defined in this way. And with this, then let us take T is your vector field. Is of course is the set value vector field we can define in this way, and then we can see that the solution of the inclusion problem, the 0 in T of X is equal to this set, and we can see also that T is our maximal monotone vector field, and by using these settings, lambda n is equal to 1 over 2 plus 1 over n, all these settings we have this computational work. So if we take T is equal to 1, and we can start U is equal to 2, and then we can see with the error 10 raised to the power minus 5, the sequence converges to 1. And the sequence converges to with the error. If we take U is equal, we fix U is equal to 4, and then we see that with the error at 10 raised to the power minus 5, the sequence converges to this at the 11th iterator. Similarly, for here, yes, we can take a T is equal to 2 and U is equal to 2. Then with error 10 raised to the power 5, the sequence converges to 1, because 1 is the solution only. So it converges to the solution at iterator 8. So here is we can have this graph for all these things. And basically, this talk was based on these 3 papers. One was published in 2019 in Journal of Fixed Point Theory and Application with Babu and Yao Professor Wang is here. Yao is his colleague. And another paper, it was published in 2020, Journal of Nonlinear and Convex Analysis. And the last one is, this paper is basically the survey article on variation equities on Hadamard manifold. It is published on in Indian Journal of Industrial and Applied Mathematics. This volume 11-2, it was in the memory of Professor Abul Hassan Siddiqui. He was my guide and my mentor, and so we have this paper in that issue of Indian Journal of Industrial and Applied Mathematics. So thank you very much. If you have any question, please.
Thank you very much, Professor Ansari, for nice talk on the non-linear version of spaces and the various topics in various inequality problems and some other problems, proximal point algorithms. So, any questions from participants or from the expert?
Amin, you are here?
Hello.
Amin.
Yes, somebody is asking.
Okay, nobody asking. Okay, no, I'm just asking.
I'm here. No,
Oh.
I'm here. Come on, let someone ask. I will ask you something. I have a question for you.
I did not ask you any questions, so you cannot ask me any question.
Hello, sir.
Yes.
Sir, I have a question.
Yes, please.
Sir, actually, you say that if the space is actually you say that there is any continuous function in the space. Hadamard, sorry, I forget this space. Any continuous has a fixed one. My question is, there is no another condition imposed.
Any continuous function defined on a compact convex subset of a Hadamard space.
Okay. Compact and convex is must.
Yes.
Okay.
It is an extension of the Brouwer fixed point theorem.
Thank you, sir.
Any other question?
I have a question, sir.
Yes, please.
Is there any work of optimization on fractal domain?
On fractal domain, I did not see.
Okay, sir. Thank you.
Hello.
Yes.
A fractal is basically some kind of the reason for which the certain behavior of the orbits. So one can see the fractal behavior, and there are some papers in the this site. But I have one not any comment, not any suggestions, just because you are expert on this area also. So in the version of the linear spaces, suppose we want to discuss about the, like in function analysis, if we want to discuss the common fixed points of the non-expansive mappings, then we can get the average, and by the average of the non-expansive mapping, we can use for getting the common fixed point. So the point is that this kind of the philosophy is here, or we will have to generate. Hello.
Yes, sir.
How can we handle the common fixed points of the mappings if we are having more than one?
Well, you see that the important thing is that most of the result, as I mentioned, which are required only the completeness, they can be extended and can be derived very easily, as you can treat the metric space same as the Romanian distance.
Okay.
Yeah.
Okay. Any other question?
Okay, I have a question.
Okay, okay.
You cannot ask.
Okay, welcome. No problem, no problem. This is the platform for the discussion.
No, I'm just joking. I'm just joking.
Okay,
Okay.
Hamar,
Yes.
let me, first of all, thank you very much for this talk. I heard it before. I don't know why. I like this one more because maybe you put it into an introductory level. Before it was too technical and I didn't follow it, but I really got my interest now. A quick question. Just for the people who are not familiar with this, is that the fixed point theory. Now I'm looking at fixed point theory, the variational problem. Okay, fixed point problem, the metric fixed point problem, not even the Brouwer and topological fixed point problem. Okay. The metric fixed point, the origin of the metric fixed point problem on manifold and specifically on cat-zero spaces goes back to the work of a Polish group. There were people working with Goebel, and there is a book, a beautiful book by Goebel and Shimon Reich on hyperbolic geometry and so on and so forth. It's beautiful. Okay, now. What happened is that these people, what they showed is that using that convexity, the convexity, the geodesic convexity, okay? And it has some behavior that are similar to the Hilbert, okay? Similar. I didn't say, we have to be extremely careful about what I'm saying and take it with a grain of salt, okay? Be careful about what I'm saying. Okay, so my point is that properties, these properties, like for example, a parallelogram identity that's not an identity is an inequality that implies the uniform convexity of the distance in the metric sense. Okay, so the point I want to ask is, first of all, what kind of manifolds for which the Romanian distance will have a good behavior? It's a very, very interesting question, where we can develop a fixed point theory for non-expansive mapping and so on and so forth. That would be very interesting.
Yeah, you are right. So far, no work has been done in this direction. Basically, you see, as I mentioned, that we are considering the Hadamard manifold because we use a certain type of proposition, so that the geodesic can be written in the form of the exponential map, and its inverse is continuous. So we have only that if we need in the metric space the compact completeness, and you see that's the contraction map, another type, even then like this Christie's fixed point theorem or this Aligarh variation principle, they are all holds good in the setting of a Hadamard manifold. But if you go beyond this one, you will go to the non spaces, then there is no work so far in this direction. Yeah, of course one can try, but it seems that it's very difficult. You should have a very good knowledge of Romanian manifold. We do not have such a good knowledge of Romanian manifold. Yeah.
Okay, thank you, Professor Ansari. There are some more scopes in the area of the nonlinear spaces. So thank you very much for nice talk. Now
okay,
I hand over the session to Professor Som.
Thank you, Professor Sahu.
Thank you. Hello, Professor Som.
Yeah.
Okay.
So really, it was a wonderful talk by Professor Ansari, and I'm really thankful to Professor Sahu also for chairing this session, and Professor Ansari for delivering a very, very illuminative talk.